Sugimoto on baryons from Instantons and Holographic QCD.
Okay, thank you very much. First of all, I'd like to thank the organizers for inviting me to such a great conference. I'm very much happy to be here for the first time in my life. Okay, I'd like to talk about these baryons from Instituto in Holographic QCD. And my talk is mainly based on this paper, which was done in collaboration with Hata and Sakai and Yamato. And also earlier proposal given with Sakai. And there's also a closely related interesting paper written by these people, which appeared recently. Okay, my plan of talk is as follows. First, I will give you an introduction and briefly review the construction of the model and some of the highlights of the model. And then explain how these baryons appear in the model. And the answer is it appears as an instanton in this model. And this section is the main result. I will present you the baryon spectrum coming out of this model. Okay, let's start. So let me start with this very elementary question that what are hadrons made of? Of course, we know the answer. The hadrons are made of quarks, like in this picture, and these quarks are described in QCD. But around 1970s, there's another proposal that the hadrons are made of strings, and this is, of course, the starting point of the string theory. But nowadays, we think that this QCD is the fundamental theory of hadrons, and this string theory is a kind of effective theory coming out of this QCD. But I think the situation has drastically changed since the discovery of ADS-CFT correspondence. Because this gauge string duality suggests that the gauge theory in four-dimensional space-time is equivalent to string theory in higher dimensions. So if the string theory dual of QCD really exists, it suggests that string theory can again be a theory of hadrons. And the problem in the old day can now be solved with the help of this D-branes, curved space-time, and holographic. So for example, the fact that string theory can only be consistent with 10-dimensional space-time is no longer a problem, and it is an advantage if we accept the idea of holography. And it is also interesting to say that both QCD and string theory can be fundamental at the same time because they are equivalent. And so we may have to change our attitude to think about the concept of elementary particles. So recently we proposed a model which seems to lie along this line. And we proposed to think about this type 2A string theory in Witten's D4-brane background. This is a non-supersymmetric background. It's supposed to be dual to pure ion Mills theory in four-dimensional space-time. And we add this NF probe D8 branes in the system. And we argued that this system is actually dual to four-dimensional QCD with NF massless quarks, at least at low energy. And the outline of the construction is as follows. So we consider, first we consider NC D4 brane with NF D8 per pairs, like in this picture. And then we see that the open string coming from this one, open string attached on this D4 brane produces this gauge field. And from the open string stretched between this D4 brane and D8 brane, we find that there's a massless mode, which is a left-hand component of the fermion. And in the same way, we find right-handed component of the fermion from the string stretched between D4 and D8 bar. And collecting these together, we obtain four-dimensional QCD with NF massless quarks. And on the other hand, if we replace this D4 brane with the corresponding supergravity background, we obtain the string theory in this D4 brane background. This is this Witten's D4 brane background. And we treat this D8 brane as a probe, assuming that this NC is much larger than F. The picture looks like this. And here this D8 brane is a probe brane, which is placed in the curved background, this D4 brane background. And in this way, we obtain holographic dual description of QCD. So the interpretation of the string in this model is as follows. So I'm not going to write down the explicit metric, but the topology of the background is very simple. It's just a 4-dimensional Minkowski space times R2 times S4. And here I write this R2 part in this picture. And this R2 is parameterized by this Y and Z. And this Z direction is the direction along which this D8 plane is extended. So this Z runs from -infinity to +infinity, and this is one of the coordinates on this D8 plane work volume. So D8 plane is extended along this X mu and Z and S4 directions. And in this sense, in this system, we have closed strings and open strings attached on this D8 plane. And these closed strings are, of course, interpreted as glue balls, and they are studied around extensively around this 1998 by many people. So I'm not going to talk about it today. And on the other hand, this open strings on this D8 plane is interpreted as mesons. And it is easy to write down the effective action for this open strings on this D8 plane. And here I only consider the SO5 invariant states for simplicity. This SO5 is the isometry group of this S4. I mean, this SO5 acts on this S4 as a rotation. And then this 9-dimensional world volume is reduced to a 5-dimensional world volume, and effective action turns out to be 5-dimensional UNF Yang-Mills-Chern-Simons theory of this form. And here this K is just 1 plus D square, and so this is a 5-dimensional Yang-Mills in certain curved background. And also we have this Chern-Simons term, including this Chern-Simons 5 form with this coefficient proportional to NC. So this action is the starting point of my talk, today's talk. So yeah, again, this 5-dimensional Yang-Mills-Chern-Simons system is the starting point of my talk. And in order to extract the 4-dimensional physics from this 5-dimensional action, we expand this 5-dimensional gauge field with respect to some complete sets. And this B mu and phi will become a 4-dimensional field. And all we have to do is to insert this expansion into this 5-dimensional action, and you will obtain 4-dimensional effective action, including these 4-dimensional fields. And the interpretation as follows. This phi 0 is interpreted as pion. This is a massless field, massless scalar field, and we interpret it as a pion. And the lightest vector field is interpreted as rho meson, and the second lightest one is interpreted as A1 meson, and so on. And in this way, this pion and rho meson, A1 meson are unified in 5-dimensional gauge field. And I think it is very, yeah, this is, I think, one of the most beautiful points in this model. But I want you to keep it in mind that our analysis is reliable only when this number of colors is very large and the Hood coupling is very large, because we are using the supergravity approximation. And also the energy scale should be small, and NC should be much larger than NF. And also in our construction, we can only construct massless quarks, and so all the quark mass are 0. So in this sense, we should not be too serious in the quantitative comparison with the experiments. But nevertheless, we find fairly good agreement, as you will see. Okay. So here's some of the results we obtained. So first of all, we can obtain the chiral symmetry breaking, and we gave a geometric interpretation for this chiral symmetry breaking. So in the perturbative picture, we had this kind of brane configuration, and this chiral symmetry, UNFL cross UNFR, is related to the gauge symmetry on this D8 and D8 bar. But after replacing this D4 brane, the picture looks like this. And now this D8 and D8 bar are connected like this. And we have only one connected component of D8. And so we have only one component of this UNF. And this is nothing but the chiral symmetry breaking expected in QCD. And also, the most surprising point for me is that this model naturally reproduces various old ideas like vector meson dominance, Gell-Mann-Sharp-Wagner model, Square model, hidden local symmetry, Wess-Minowit-Enter, Witten-Venetian formula, and so on. And we also made some numerical analysis for the masses and couplings of the mesons, and yeah, surprisingly, they agree with the various experimental data. So here's some of the results. For example, this is the mass of the raw meson, vector meson and actual vector mesons, and this is the experimental data, and this is the numbers came out from our model. And for the couplings, these are our calculations, and these are experimental data, and so you can see that they roughly agreed. So yeah, some of them do not agree well, but I can say that the agreement is much better than expected, because our analysis is very crude. Okay, so the meson sector seems very nice. What about baryons? So the construction of baryon is also very simple in our model. And actually, we can apply the construction of baryons proposed in the ADS-CFT context by these people in 1998. And in our case, this baryon is constructed as D4 brane, wrapping on the S4, non-trivial S4 in the background. And so we obtain a meson as a fundamental string and baryon as a D4 brane. This is a soliton in the string theory. And these people also showed that NC fundamental strings should be attached on this D4 brane. And so this picture looks very much like this quark model picture. This meson is a bound state of QQ bar, and this baryon is a bound state of NC quarks, if you interpret this fundamental string as a quark. And on the other hand, as I told you, the effective field theory for this open string on the D8 brane is reduced to 5-dimensional gauge theory. And this meson came out from this 5-dimensional gauge field. And we can show that this baryon expressed as D4 brane is now constructed as instanton in this 5-dimensional gauge theory. And this is what I'm going to talk in the following. And it is also interesting to say that if you reduce this 5-dimensional system to 4-dimensional system, only massless mode is pion. And if you reduce this instanton to 4-dimensional system, the skyrmion naturally came out. So this is nothing but the baryon construction proposed by Skyrm in the 60s. And so this instanton description of baryon is closely related to the skyrmion picture. Okay, here's a summary of the rest of the talk. So we propose a new way to analyze baryons that extends Skyrm's old idea, including contribution from vector mesons. And baryons are, the main message is that the baryons are described as 4-dimensional instantons in the 5-dimensional gauge theory. 4-dimensional means that 4-dimensional spatial directions. And we also analyze the quantum mechanics, and the quantum mechanics on the instanton modular space gives the baryon spectrum. But I have to say that the quantum quantitative tests are not good yet. So please be generous today. Okay, let's start. So this is what I've already told you, but let me repeat once again. Consider instanton configuration in this 4-dimensional spatial direction. So we are considering 5-dimensional gauge theory and considering the static field configuration, and consider instanton on this spatial 4-dimensional space. And if you consider a point-like instanton, like in this picture, it behaves like a point-like particle. And we interpret this particle as a baryon. And in fact, it is very easy to show that the baryon number is given by this instanton number carried by this gauge field. And this, the previous description as a baryon as the D4 brane wrapped on S4 is actually equivalent to this instanton on this D8 brane, because this instanton on this D8 brane is equivalent to D4 brane on this D8 brane. So in this way, we can show this equivalence. And also, as I told you, this instanton is related to skyrmion, and we can actually show that this instanton number is equivalent to the winding number for the skyrmion. And in this way, we can show that these three different descriptions of baryons are actually equivalent. And it is also interesting to note that the realization of this baryon as an instanton is proposed in late 80s. And they proposed this kind of formula. And if you insert the instanton in the right-hand side, you will obtain the skyrmion in the left-hand side. And at that time, this d direction is just a mathematical or mathematical coordinate and introduced as a technical reason. But in our case, this d direction has a definite physical meaning because this d is one of the coordinates on the d8 plane work point. Okay, let's try to solve the classical equation motion. So it turns out that the instanton solution for this Yang-Mills action, given by this action, shrinks to zero size. So the picture looks like this. If you write the size of the instanton in the horizontal axis and plot the energy carried by the configuration, you find this kind of picture. And it is easy to show that the minimal energy configuration is actually the zero size instanton. So this is a little bit discouraging because the zero size instanton is a singular configuration, and so defective field theory like this can no longer be trusted for this point-type instanton. So what do we do? So actually we are missing something. So we have to include the effect of Chern-Simons term, and as I told you, we have this kind of Chern-Simons 5 form in defective action. And from this Chern-Simons 5 form, we have this kind of term. And here this AU1 is the U1 part of the gauge field. And for the instanton configuration, we know that this part is non-zero. And from this part, term, we see that this term acts as a source term for this U1 charge. And we know from the electrodynamics that the point-like charge costs energy. And so we can expect that the size will be stabilized with the non-zero final value. So the picture looks like this. So again, the horizontal axis is the size of the instanton, and we plot the energy. And this line is the line that I showed you in the last slide. And if you add the U1 contribution for the energy, it looks like this. And the total energy has a minimum with finite size. And again, this has already discussed in a paper in 1984. This stabilization mechanism is the same as the stabilization of skyrmion via omega meson proposed by these people. These people showed that the skyrmion can be stabilized even without the skyrm term if we include the effect of this omega meson. And actually, this omega meson is included in the U1 part of the gauge field in our model. So the mechanism is essentially the same. And actually, we can show that the size of the instanton is order 1 over, lambda to -1/2. And it is convenient to rescale the spatial coordinate by this same factor. And after rescaling this coordinate, we can show that the leading order term is just a Yang-Mills theory in the flat space. This is because the size of the instanton will become very small if this two-Hooke coupling lambda is very large. And so if the size of the instanton is very small, we can approximate the space-time as a flat space. And so the leading order classical solution is well known. It is just given by this PPST instanton, and the instanton configuration, the configuration of the gauge field is explicitly known. Here this rho is the size of the instanton, and this x and z are the position of the instanton in the x or z axis. So yeah, we basically work in this 1 over lambda expansion, and yeah, this is a solution that we are considering. Okay, let's move to the baryon spectrum. So let's consider a slowly moving or rotating baryon configuration and use so-called modular space approximation method. So this basic idea is as follows. This X alpha is the coordinate of this instanton modular space. And basically what we should do is to promote this X alpha to a time-dependent variable. And we insert a gauge configuration given by the classical instanton solution with this time-dependent moduli parameter. This parameter is also called the collective coordinate. And we insert this gauge configuration into this 5-dimensional action and obtain the quantum mechanics for this X alpha. Actually, we have to do a bit more complicated than this because we have to deal with the gauge symmetry. But I'll skip all the detail. And this is basically what we should do. And for the SU21 instanton, the modular space is explicitly known, and it is given by position of the instanton and the size of the instanton and SU2 orientation. And the quantum mechanics obtained in this way looks like this. Here, this G alpha is just a metric of the instanton modular space, and this is also explicitly known. And in addition, we have this potential term, which depends on this rho and Z. For this X and A, there's no potential like this, and we can say that these modes are J moduli in the usual sense. But on the other hand, this rho and Z has this non-trivial potential, and so they are not moduli in usual sense. But we include this the contribution from this rho and Z because we can see that these modes are light compared with the other massive modes for large lambda, because if lambda is very large, this is almost flat. So solving the Schrodinger equation for this quantum mechanics, we can obtain a baryon spectrum. And this generalizes the famous paper of this Atkins-Napi-Witten, who did the same thing in the Schrodinger model. But here, remember that in our 5-dimensional gauge field, 5-dimensional description, vector mesons and actual vector mesons are naturally included. And so in our analysis, the contribution from vector mesons and actual vector mesons are included. And also we included this rho and Z mode, and so from this we can expect that we can obtain something new. Okay, here's the result. So first note that we only obtained this I equals J state. But this is nothing new. This is already shown in this Atkins-Napi-Witten. But unlike Atkins-Napi-Witten, we have parity odd states. This comes from the excitation of this Z mode, which was not included in this Atkins-Napi-Witten. And the mass spectrum can be obtained like this. Here, this L is related to the isospin or spin, and this is odd numbers. And n rho is related to the excitation of the size of the instanton, and nz is related to the z excitation of the Z mode. And if you want to compare this spectrum with the experiment, this is what we obtained. So this is mainly our main result. And so here this Jp means that the spin J is spin and P is the parity, and for this it means that spin and a half positive parity state, and this is spin and a half negative parity state, and so on. So what do you think? I hope you think they are similar. So here note that we only consider the mass difference because the order 1 contribution for the constant term, this m naught, is not known. And so we just wrote the mass difference in this picture. So if you want to see some numbers, it looks like this. But this is just for illustration, and I don't want you to take this seriously. But anyway, if you choose this MKK to be 500 MeV and choose this M0 to fit the value of nuclear mass, we obtain this kind of numbers. And on the other hand, the I equals J states from particle data group looks like this. So it looks similar, right? So let me point out some interesting feature that seems to be captured in this model. But I add this question mark here because I'm not so sure about it. But let me try. So if this is again the table from the particle data group. This is experimental data. And if you look at these two or these two or these two, it seems to suggest that the parity, positive parity and negative parity states are really degenerate. And if you compare these two, the mass of these two baryons or these two, they are almost the same, roughly 200 to 300. And if you compare this one and this one, it's like 300 or 400. This one to this one is again a 300 or 400. This one doesn't look good, but if you compare this one and this one, it's again 300 to 400. So I'm not so sure, but this is the feature that we obtained in this our mass formula. And another interesting point is that if you look at these two states, we see that this positive parity baryon is lighter than this this negative parity baryon. But the phenomenological Hawk model predicts that this negative parity one should be lighter than this positive parity one, like in this picture, like in this formula. And this has been a kind of long-standing puzzle in nuclear theory. And recently, some people, these people, studied the mass of these baryons by using lattice calculation, and they suggest that they can be almost the same mass. But this feature also naturally appeared in our model, like here. But again, we have to. I have to make some negative comments. The predicted baryon spectrum looks very nice, but there are a lot of reasons that we should not trust these values. For example, we employed this 1 over lambda expansion, but it may not work well, and also we neglected all the higher derivative terms, which may become important in our case, and they are all neglected here. And also, this NC equals 3 is of course the realistic value of the color number color is not large enough, especially for large quantum numbers. So L equals 3 is already dangerous. And we know that the model deviates from real QCD at high energy, and most of the baryon, or all the hadrons, all the baryons are very heavy, and so we cannot trust our calculation anyway only from this reason. And what is most annoying for me is that the value of MKK was around 950 MeV in the calculation of meson sector. But previously I showed you this table is given by this MKK around this 500 MeV. So I'm not sure how to resolve this discrepancy, and yeah, so clearly we need more investigation for the quantitative test. So I'm almost done. This is summary and outlook. So again, I repeat that the baryons are described as 4-dimensional instanton in 5-dimensional gauge theory, and we propose a new way to analyze baryons that extends Schrödinger's old idea, including contribution from vector mesons. And as I already told you, there are a lot more to do to improve the analysis. For example, we may have to solve the equation motion numerically or include higher derivative terms, and there are a lot of corrections that we may have to take into account. And also, I want to mention that it would be very interesting to investigate other static properties of baryons, like couplings or charge radii or magnetic moments and so on. And these people analyzed along this line and gave some numbers for this charge radii or magnetic moments. And yeah, I'm sure this is one of the directions that will be interesting to investigate. Okay, I'll stop here. Thank you very much.
Thank you very much. Yeah?
So I have a couple of related questions about your probe approximation. So the first one is that because the 8 branes are codimension 1, you can't really, in principle, neglect the back reaction. The second one is that since they source the dilaton with the same sign, you can't really put them on a circle. So I was just wondering if you had any thoughts about that.
Yeah, a lot of people ask the same question to me. But here, we are only considering the probe approximation, and within this leading order of this NF over NC expansion, nothing happens. But yeah, of course, as you said, you are worrying. Once you include this correction, NF over NC correction, we have to worry about that. But we haven't look at the defect seriously.
I guess what I'm wondering is to what extent setting NF over NC is an approximation to some well-defined framework. Since
could you say that?
Yeah, what I'm saying is to what extent is setting NF over NC to 0 as a first approximation is an approximation to some well-defined framework.
Yeah, of course this is not a good approximation to compare with the real world. But at least if you take only the leading term of this NF over NC expansion, you don't have to worry about the dilaton tadpole, NF tadpole. Because the defect of the back reaction of this probrane is proportional to NF. And of course this NF appears as a combination like this, NF over NC. And so if you are only considering the leading order, you don't have to worry about it. But of course, if you want to improve this approximation, and if you want to include the subleading term, you have to worry about it, and it should be an important question to answer.
Further questions? No, then let's thank the speaker again.